Hello everyone, my name is Artem Grigorev, I am a CTO of Toloka, and today I'm going to tell you about what challenges we face and overcome while scaling our system under the load. But first of all, a few words about myself and the service. It's me. I started my career as a software engineer, used to write backend on Java. I developed different services related to data production infrastructure for various industries, and now I am CTO at Toloka. At home, I'm married and have a 3-year-old daughter. I like to travel and make photos. Speaking about Toloka, it's a global tech company that offers a data-centric environment to support fast and scalable AI development with the help of human insight. Toloka's capabilities are rooted in the intelligent technologies, a diverse global crowd, and a secure infrastructure to support the most demanding projects. Data collection and labeling platform is one of our core products. The platform connects two sides. On the one hand, our clients, such as different machine learning teams, post tasks to get data. On the other hand, millions of annotators perform those tasks and get paid. We call these users Tolokers. Just to understand the size, I give you some numbers. Every day at Toloka, more than 800 projects run, more than 50,000 Tolokers complete more than 16 million. My talk will be mostly about Toloka's internals. I'm going to tell you about one task we are solving. And to attract more attention, I called it the main task of Toloka. Anyway, this task describes the course scenario for Tolokers, and there will be 3 stories about different stages of the process, and as a result, we will make conclusions. I hope my talk will help you with designing and developing your systems in the future. Let's formulate the problem first. The slide shows how the platform works. Everything is super clear and simple. As an input, we have tasks. As an output, we provide results. So basically, Toloka is a huge computing cluster, but nodes in the cluster are not computers, but human brains. And the problem we are trying to solve is the problem of managing the cluster and distributing tasks in order to get the best results with the maximum throughput. We cannot manage the cluster directly. The only way to do it is to show for each user a list of tasks available for them. And then users are free to choose any task from the list which they like. So by creating these lists, we manage the distribution of tasks in the platform. Under the hood of these cards, we have 2 basic types of entities. And then each project contains a queue of pools, batches of data that our clients upload to Toloka. So the problem is how to choose those pools which are available for the user, and therefore how to form the list of tasks. As an example, available pools are highlighted on the slide. Where is the complexity hidden? It seems to be quite a simple problem. Here come users, we show them some data. Yes, most of the systems are quite straightforward. So requests from users to data are distributed like shown in the slide. Such systems are quite easy to scale via sharding. You may split the data by shards, you may replicate the data and create several instances of backend responding to user requests. But it is much harder for Toloka. Here we have a case of a complete bipartite graph, which means that every user can theoretically access any pool in the platform. So for example, in the task of checking availability, we must do it for each Toloker and for each pool. If we split data by shards, a request would visit all shards. If we split by users, we would have to copy the same data on all shards. But as Toloka operates with money, consistency requirements automatically arise, and we wouldn't be able to maintain data consistency over so many replicas. As you see, even not so high load from the number of users' perspective, multiplied by the number of pools active in the platform, leads to a heavy stream of requests and computations in the service. So here's the problem. How do we solve it if we can't scale via sharding? So what to do then? How to make shards out of the system which is impossible to split? Our approach is to decompose the whole problem into 3 stages, and to find specific scaling point for each stage. Further, I will tell you about all 3 steps in detail. The first stage is filtering. On the slide, you may see a part of our user interface as it's shown to our clients who put their task into Toloka. There is a feature of setting a target audience for each pool. For instance, here you see that this pool requires users who know English or French languages, who live in the United Kingdom or France, and who has some skill greater than 65. Skills are like variables attached to each Toloker, For instance, they may represent estimated quality of doing different types of tasks. For each pool, we have a predicate, which is applied to user parameters and tells us if a pool is available for this user or not. Initially, we used JS Query, an extension for PostgreSQL designed to compute such predicates efficiently in the database. But later, this simple solution stopped working because of increased load, so we decided to move computations into the backend, which is cheaper to scale. Of course, the number of users continued increasing, the number of pools increased too, so multiplication one by another led to a huge load on our backend. Probably the most obvious solution that allows decrease the number of computations is caching. But in our case, it was a tricky decision what to cache, because all those predicates are created by users, so they can have any form. A DNF, disjunctive normal form, came to help us. Any predicate can be represented as a DNF, multiple ORs on the first level, and ends on the second. You may see on the slide how the predicate on the left from the example is converted into a DDNF in the right. We decided to use a conjunction plus its argument values as the key for the cache. Since those simple parts are not quite variative from pool to pool, and states of Toloker's profiles don't change frequently, the solution helped us significantly reduce the load on our backend CPUs. As an illustration of this stage, I am showing you a graph representing the number of simple checks done per second during a week. As you see, it's on average 100,000, but we keep a reserve here because sometimes we experience the load increasingly like 10 times or even more. The second story is about the next stage of the process. If we explore a pool, we see that it consists of atomic tasks. For example, in case of data labeling for machine learning, each task is equal to a single object to be labeled. It may be an image, a text, or something else. If the pool is available for Toloker by filters, it doesn't mean automatically that they can do any task inside. For example, a Toloker can do a task twice. So as a result, on the second stage, we run availability checks for each pool on its tasks level. We tried a few naive solutions, optimize queries via batching, cycles, stored procedures, but then we hit the limit of main server performance. We switched to replicas, got and overcame issues with data consistency. But anyway, we faced the same problem as we did on the stage 1. Too many checks. But unlike the first stage, caching can't help us here. The state changes continuously because users do tasks, so they constantly become unavailable for others. What could we do? Yes, if we can cache anything, let's try not to compute something at all. In other words, lazy evaluation may help us here. On the slide, I outlined all checks made previously. But not all pools have the same priority. There is a queue of pools for each project. So we can check availability not for all of them, but by layers. At the beginning, we check the first layer with depth of 1. If any pool matches, we stop checking the line at all. Then we check the next layer, increasing the depth. Looks great. Here we see a graph of load on our PostgreSQL database cluster. Now it consists of the main server and up to 10 replicas. And here you can see how the CPU usage all over the cluster was changing during a 3-month period, from dozens to 100+ cores. But again, to be ready for peaks, we also keep the reserve. At the beginning, I said that our problem couldn't be solved by sharding, but of course we will eventually come to that decision. Maybe we could weaken consistency requirements or try to find a fuzzy solution for checking the availability of tasks. And the last story is a bit different, but also interesting in terms of scaling issues. Usually thousands of users have access to the same pools. And in some cases, we don't need so many of them labeling the data. Therefore, it would be nice to leave only some top performers and gain the best quality of results. This is also beneficial for users, because when they choose a highly competitive project, each Toloker gets only a few or even none of tasks, which is frustrating. Toloka has a feature that allows our clients to set a percentile of users that will have access to the pool. We have a machine learn function that predicts the quality of a Toloker on a pool. Let's say that each pool has a function that can predict quality of results by a given user. At any moment, we want to understand if a Toloker belongs to the desired quality percentile. Depending on that, the platform will show the pool to these users or not. To solve this problem, we use the data structure of Redis database called sorted set. It is like a cache that can easily respond to queries which position in the given order an entity belongs to. For each pool, we store a sorted set structure of users, and also we store a separate set of users sorted by the last activity time. It helps us to keep active users only, not all Tolokers. When a request comes, we calculate the quality predictions for each pool. Then we get positions in sorted sets, make marks where we have certain percentiles, and then check if the user belongs to the top for each pool. If not, then the pool becomes unavailable for the user. And also each user user request will update the structure which stores the active users. And in the background, we remove from all sets those users who were last active earlier than X minutes ago, like in the slide. So initially, we inserted into all sets in a cycle, but single inserts worked quite long due to network delays. Then we used a feature that allows to execute one script with all inserts for the cluster, but unfortunately such scripts don't work if they touch more than one shard. So we reverse engineered how Redis calculated the shard index by a key, and instead of sending one script for the whole cluster, we split it into few scripts, one per each shard. Here's the graph showing the number of operations executed on the Redis cluster during a week. As a side note, I'd like to say that the solution we made already contains a way to further scaling. Once the size of a set increases, we will split it into two sets and solve the task approximately. If users are uniformly distributed between those two sets, checking if a user is in a percentile on one set is approximately equal to a check on the union. It's time to wrap up and make conclusions out of the talk. We considered the problem how to form a list of available tasks for Toloker. The task itself is hardly scalable, but we decompose it into 3 stages and found a scaling point for each stage separately. Let's remember what helped us. Firstly, moving load on replicas obviously helps wherever you cannot move computing on backend. Caching helps if you have a lot of similar calculations. Lazy evaluation is applicable if there is an order in calculations and some of them are less important. And at the end, the last solution was scalable by design because of sharding support and future scaling plan. I also have some more philosophical statements. I hope my talk will prompt you to think about calculating points. And most of services have a relational database as a load consumer, but unfortunately, relational databases are really hard to scale. So if your service is going to grow, it's better to think about logical sharding on the design stage, because later it would cost much more efforts. And if your service isn't supposed to grow, it is not interesting to build it, is it? If you didn't follow the previous advice, you may try to scale via distributing load on replicas. But you will face issues with consistency, synchronization, and so on. Also, keep in mind that queries on replicas might run slower because indexes. And of course, you won't be able to add new replicas eternally. I highly recommend to dive deeper and understand how technologies you use are implemented. How properties of entities in your system can help you make everything better, more reliable, and scalable. That's it for today. Thank you for listening.